Last week, we started looking at the first derivative test. Okay, just kind of review where we've been here. And the first derivative test is really a very small extension of what you did like on your homework, right? Well, we did that for max and mins on the homework with using your increasing and decreasing and using your sign analysis. Because we said if the derivative goes positive to negative, we have a max. If it is decreasing and negative to positive increasing, we have a min. If there's no sign change, we don't have a max or a min. And then we also have the final one, which is one we don't use a whole lot, which is at endpoints. So we looked at all these different kind of things. You know, here is an example of something that is positive, 0, positive, no sign change, so you don't have a max or a min. Is there still a critical point there? Yes. So even though you don't have a max or min, you still have a critical point. So where do you look for max or mins? At your critical points. Those are the places you investigate to determine is a critical point a max or a min or no extreme. We only have to worry about those points. Okay. We did our sign analysis by finding our derivative, finding our critical points, determine where it's increasing and decreasing, and then determine our max and mins from that. Okay, so this is kind of what you were doing on your homework also. Okay. We also talked a little bit about the second derivative test. The second derivative also tells you max and mins. Okay, we'll get to that when we get there a little bit later. Okay. All right. So let's talk about concavity. We want to get into the concavity a little bit, okay, today. So concavity. We don't talk about concave or convex or like that. We look at this as either concave up for something that opens up, concave down for something that opens down. Okay. So something is concave up when the derivative is increasing. Something is concave down when the derivative is decreasing. How do we determine where a function is increasing? Sign analysis of the derivative and you find your critical points, right? How do we determine where the derivative is increasing? Second derivative, and we're going to do sign analysis of the second derivative. So it's very similar to what we did before, where we find the derivative of the first, critical points, and then do sign analysis. However, this time, we're going to do that with the second derivative. Okay. Now, where our second derivative is positive, it's concave up. Where our second derivative is negative, it's concave down. Now, as we do that, here's how I remember this, okay? I think of this all based on x squared. Because you all know what x squared looks like. It's concave up. And we know the first derivative is 2x, the second derivative is 2, which is greater than 0. So I think all of you are smart enough to take the second derivative of x squared pretty quickly in your head. So do x to 2. So because of that, this is a great thing to remember for what the shape it opens up. Because you can do that really quickly in your head. Okay? Notice, this is turning concavity. This is using the second derivative. This is not the second derivative test. That's confusing. The first and second derivative test only tell you max and mins. So we do more examples, maybe this will become clear. Okay, so here we go. Find where 2x cubed minus 4x squared is increasing, decreasing, local extrema, and concavity. Now, we already did this previously, right? This is an example we did in the front of your notes. So from the front of your notes, what was the derivative? Somebody flip it over to the front. 6x squared minus 8x. Where was it increasing?
4/3 infinity and -0.
And then it was down 0 to 4/3. Our max was 0, 0. 4/3, negative 2.36. So that's all the stuff we did earlier in our notes last week, right? So we found all that already. So now let's add the concavity to it. So to do concavity, I want to take the second derivative. Second derivative is 12x minus 8. We want to set that equal to 0. And we get 2/3. Now, what do we call that point? No. No. What do we call when we set the first derivative equal to 0? Our critical points were 0 and 4/3. Now what do we call it when we set our second derivative equal to 0? Unfortunately, they literally have no name for those. So I'm just going to make up a name.
Okay.
I'm going to call it special point.
Special point?
I'm just going to call it like a special point. Or do you have another name? What? Or we just give it a name, Steve's point, whatever, Bob's point, whatever. So, I don't think, so I don't think, there's really no name for that. Now, jump ahead what Carter said, inflection point we're going to get to, but is every critical point a max or a min?
No.
No. Is every special point an inflection point, which I haven't defined yet? No. So an inflection point is kind of like max or min, so that's coming. So here's what we have to do. We have to do sign analysis of the second derivative. Our special point is 2/3. So if we have 12 minus 8, if I pick something less than 2/3, 0. Do I get a positive or negative? Negative. If I pick something bigger than 2/3, like 1, I get a positive. So we now have our concavity. It is concave up, where it is concave up positive or negative? Positive. So this is 2/3 to infinity. Concave down, negative infinity to 2/3. What's that? Now, what this leads to is our last thing we want to talk about, which is an inflection point. And you can see in your notes, what is an inflection point? An inflection point is where the concavity changes. Okay. It's where our concavity changes. Okay. So here, our inflection point will be 2/3. Do I plug that back into the second derivative, first derivative, or the original function? Original function, because it's a point on the graph. So if we substitute that back into our original, someone do that in a calculator for us? Let us know what you get.
1627.
What is it?
I don't know. I'm just trying to do something in my head.
Oh, so we get 2x cubed. Yeah. Anyone?
No, boys. Yeah, second. Mike, what do you do? I do it in my head. Hold on a second.
Good for you.
First one's 28 for Peter.
First, oh, you mean the first part of it?
Yeah. Wait, no. Oh, I did that wrong. Oh, my word. Hey, give me a second. I need to bust it. No, I didn't see that. You already lost. Blind
Negative 1.185.
Negative 32 over 27. Or negative 1.185.
Okay.
So, now, let's say we wanted to take all of that and try to sketch a graph. Right? So we understand
Never want to do that.
how all of that fits together.
You didn't know what it did.
All right, so let's talk about how we can use all of this to get our graph. So if you want to sketch a graph, first, let's mark our max and mins. We have 0, 0 is a max. We have 4/3, negative 2.36, which is 1/3, negative 2.36, which is right there. Those are our peaks and valleys. Our inflection point is 2/3, negative 1.1, so that is 2/3, negative 1.1, which is right there. All this connects together. Over here, from here to the left, it is concave down. From here to the right, it's concave up. So if you combine this with your increasing and decreasing, it's increasing here, decreasing here, but all of that is concave down. So you get to that. Here it's decreasing and then increasing, but it's concave up. Like that. So besides just increasing and decreasing, we now also know the concavity. And you can have, if you look at the graph here, this point right here, 2/3, negative 1, that point right there is called our inflection point. Our graph changes from concave down to concave up. We talked about that inflection point last week in statistics.
We did.
Because we talked about the normal curve, and this is mean, and if you go one standard deviation, you're not in stats, don't worry about it. We talked about how those points right there, one standard deviation, how here it was concave down, and then here it was concave up.
Oh, I do remember.
Connects with that.
Yeah.
Okay. All right. Understand, you can kind of have all of these combinations. What do I mean by that? You can have concave up and it's increasing which looks like that. You could have increasing but still be concave down. That's increasing, but it's concave down. Still increasing, concave down, increasing, concave up. You could have decreasing, concave up. You could have decreasing, concave down, which would be like that. So the concavity kind of gives us that like arc, so to speak, of the graph, besides just increasing and decreasing. It's which way, because it could be increasing like this, or it could be increasing like that. Concavity gives us that extra piece of information as we try to graph. Okay, we try to get our accurate graph or function. Okay. All right. Let's go to the back. This is a question I really like, because you have to understand all of this to be able to do this, but you can't use your calculator. So we want to graph a function, f of x, that is continuous. What does it mean to be continuous? Don't pick up a pencil, right? That's the informal, but that helps us here. So you have to be able to draw this. There should be no holes or gaps or vertical asymptotes or breaks, okay? It's decreasing and concave up on negative infinity to negative 3. It's decreasing and concave down on negative 3 to 1. It's decreasing and concave up on 1 to 2. It's increasing and concave up on 2 to infinity. Sketch a graph. Go. And then we'll pick somebody to come and put their answer up here and see how they did. Let's go through this. I'll explain how I would do this. I would start over here. I'll start at the far left. Negative infinity to negative 3. It is decreasing, concave up. So here is my negative 3, right? So it is decreasing and concave up to there. Looks like that. From negative 3 to 1, it's decreasing and concave down. From 1 to 2, it's concave up and decreasing. And then from 2 to infinity, it's increasing and concave up. Or something like that. That is not a very good, this part right here. Right there, 1 is my inflection point change, right? You get something like that. Notice, does it have to look like that? That kind of the shape, but if you think about it, I didn't say anything about where this is at. This could be like down there, right? Or this could be way up here. The y values don't matter here. It's more, these are all the x values wherever you put it. Okay. I like that kind of problem because you have to understand increasing, decreasing, concave. You have to understand what all of this means when you graph it, but you can't just type it in your calculator and see what it looks like to verify. Okay. All right. So, as we talked last time, I'm going to come back to that. We have our second derivative test. Our second derivative test is connected with concavity because our second derivative test says if the second derivative is 0, you have a min. But if the second derivative is 0, what's the concavity? If its second derivative is positive, it's concave up. So if you're concave up, what's your point? A minimum. If it is concave down, when it's negative, you have a max. Now, that seems backwards. Because you, in my mind at least, if it's positive, I kind of consider positive to be a max. Negative seems to be a min. Doesn't that kind of fit how you think it would go? But it's the opposite. And so I go back to that x squared, right? If my function is x squared, my second derivative is 2, and I know what x squared looks like. It has a min, which helps me remember that. So anytime you're dealing with concavity and second derivative, I always think x squared is kind of my baseline that I can quickly do in my head to keep everything straight. Okay. All right. So as we talked about last week, you know, if you want to do second derivative test, if the question is find where it's increasing, decreasing, would you ever do the second derivative test? No, because you already have the sign analysis done for increasing and decreasing. You just use first derivative test to find your maximum. If you don't have to do that, if the question is just what's your max or min, sometimes the second derivative can be easier. So you can kind of do it either way. Okay. All right. Where's the problem? There's one more problem on your nose, isn't there?
Yeah.
But all right, we have that. So here's what I want you to find. 1, increasing and decreasing. 2, max and mins. 3, inflection point. 4, concave up and concave down. Critical points are -2 and 4. So my special points are 1. I do my sign analysis of my first derivative. Do my sign analysis of my second derivative. Right there. So positive, negative. This is a max, negative, positive. This is a min. Now, if I write all this down, I am increasing negative infinity to -2, and from 4 to infinity. I am decreasing from -2 to 4. I am concave up from 1 to infinity. I am concave down from -2 to 1. I have a max at -2. I have a min at 4. And I have an inflection point at 1. If I take -2 and I plug it back into the original, what you get is your max. Anybody? 60. If I plug 4 in, my min is -48. If I plug 1 in, I get 6. Is my function. Yes. So if you think about it, one way to think about this, the max is really the point -2 f of -2. Because the max and min and inflection points are points on the original graph.
Right.
So you plug them into the
I
original.
might have got, I got negative 20.
Negative 20 for,
I think I negative 20. I got 6.
I got 60. You're wrong. I also got negative 48 and 6.
or you all made the same mistake. I mean, that's possible.
I think I negative. Negative 2 squared is negative 8. How did I got negative 8 minus 12 plus negative 2.
Let's consider this for a second, okay? The question was, how do you know if a special point's an inflection point?
Oh, okay.
Consider this function. Okay? My derivative is 4x cubed. My second derivative is 12x squared. So what's my critical point? 0. What's my special point? 0. So my critical point is 0. My special point is 0. But if I did sign analysis, this is minus plus. Here, this would be plus plus. There's no sign change here. So is 0 a inflection point? No, there's no sign change. So there's no inflection point. Which makes sense because this graph looks like this. This is x to the fourth. So you have a minimum right there. But does the concavity ever change? No. So that's how you could have a special point.
So the sign analysis, the second derivative tells you where maybe changes it.
It tells you where it's concave up and down, and if there's no sign change, there's no concavity change, and so there's no inflection point. It's similar to when, did we do an example? You go back. Where's the graph? The graph here. It's similar to here. We have a critical point here where it's 0. But if you did a sign analysis, it's positive to positive, and so there's no sign change, so there's no max or min. Now, if there's no sign change, whether it's positive, it could be negative, negative if it's going down, like over here. Negative, negative, there's no sign change, no extreme value for the first derivative. No sign change for the second derivative is no inflection point.